Hi there. Today we'll look at linear transformers are secretly fast-weight memory systems by Emanuel Schlag, Kazuki Airi, and Jürgen Schmidhuber. On a high level, this paper makes a connection between linear transformers, which are transformers that linearize the attention mechanism, such as the performer, and fast-weight memory systems, which is a bit of an older concept where fast weights refers to one mechanism producing weights for another mechanism. So like a neural network producing weights for another neural network. The first neural network will be called the slow weights, and the produced weights would be called the fast weights. So the paper makes a connection between specifically autoregressive linearized transformers and these fast weight memory systems, and looks at it in terms of how much memory are they able to store in these weight matrices, and it analyzes it and proposes a new update mechanism for autoregressive transformers, and then demonstrates kind of the effect of that in experiments. We'll go through the connection they make and look at their new method, their new proposed linearized attention, and we'll look at the experiments, and that will be the paper. So if you like content like this, please share it out to all your friends and enemies, because love is okay. I'm becoming Lex Friedman. So what are fast weight systems? Fast weight systems, as I already said, is when one neural network or one mechanism produces weights of another neural network. So the fast network would not be learned per se, but it would get its weights from the slow neural network. And this here is an example of that. By the way, new recording setup. Thank you for your feedback very much. So I have extended the screen here to cover the entire area. Please, more feedback. I know this is still pixelish. If anyone knows how to make OneNote not do pixelish PDFs, please tell me. All right, so here is one of these fast weights mechanism. So a slow net with slow weights continuously generates fast weights for a fast net, making the fast weight effectively dependent on the context. Simply put, the slow net learns to program its fast net. And here in these papers by Schmidhuber, he proposes these outer product fast weight systems. And here is how it works. So imagine you have a sequential input. So xi is going to be x over time. Remember, we're in the autoregressive setting. So the autoregressive setting is where you have a sequence as inputs, and then from that sequence, you're trying to produce the next element of the sequence, for example, in language modeling. And then in the next steps, you take that next element into your context and you produce the next element, and so on. So that goes on, and that is the autoregressive setting. So we are wondering, how do systems produce, in these autoregressive systems, produce their outputs? And one way is this fast weight system. So imagine you have these x's here, which are the input sequence. So we're going in terms of an input sequence. How do we produce the y how do we produce the next input, or specifically in a more general setting, we have an input sequence and an output sequence, and at each step, we kind of want to produce the corresponding output. So in the first step, this, and then in the second step, we already have two inputs and we produce this output. And in the third step, we have three inputs, we produce the third output. We have three inputs. And in the fourth step, we have all four, we produce the fourth output. Of course, in the autoregressive setting, we would every time take the output and plug it in here at inference time, not at training time. All right, so I have input sequence and output sequence. How does each step look such that we produce the corresponding output? Well, here's what we do. We have these matrices called W. And the W matrices are these fast weights. And you can see the output is simply produced by taking the current input and multiplying it in a linear fashion by the fast weight matrix. Okay, so right now, if you just look at this is simply a linear transformation. The magic happens if you consider how these weights here come to be. So these weights are now going to contain the entire context of the past inside the weights. So other than, it is a bit like a recurrent neural network where you have a hidden state, except here the weights themselves are the hidden state. So how do you generate the weights here, these fast weights? Well, these fast weights are produced by updating the fast weights of the last step. You can see right here, and here is where the recurrence comes in. So the fast weights of the current step, that's not supposed to happen. The fast weights of the current step are produced by adding on top of the fast weights of the last step. There is a nonlinearity involved right here, but essentially you take the last fast weights and add something to it. Now, what is that something? That something is here this outer product of these vectors A and B, which are themselves constructed by taking the input and running them through their own neural networks, or just their own linear transformations right here. You can see that this mechanism will continuously produce weights. So there is a few intricacies here, like this is the outer product between the vectors, and that's needed because in every step you want to produce a valid weight matrix, right? And this is how you produce a valid weight matrix, by taking the outer product. If now you accumulate those outer products essentially in these fast weights, which has some other interesting properties, and the paper is getting to those properties later here when it talks about tensor product representation theory. But essentially, this is how people store information inside of matrices. It's a bit of magic, but imagine you have keys and values, and you want to store those keys and values like in a database, but you want to do it in kind of a continuous manner. So this comes from a time when people were trying to bridge the symbolic world to the neural network world, let's say. So they were trying to put discrete things or objects and symbols into distributed representations like vectors. So if we want to build a database, what we have to do is we're going to have keys and values that we store, right? Key 1, value 1. Key 2, value 2. This goes all into a database. Key 3, value 3. And if we then come and we query the database with one of the keys, like, okay, I have now key 2 is my query. I define my query as key 2, and I go to the database better give me value 2. How can we implement this as a distributed representation database? So first of all, imagine we are going to have keys and values. They're all going to be vectors. So the keys are going to be represented as vectors, and the values are going to be represented as vectors. Okay, the key may be this vector, and this vector here, and the values this vector, and this vector. Okay, we can do symbols to vectors by doing embeddings. So we know how to obtain that. But now how do we implement the database? Well, if I'm just going to show you what I can do. How do I build the database? I'm going to build the database as follows. I'm going to take key 1, and I'm going to do the outer product to, that's a plus. I'm going to do the outer product between key 1 and value 1. And then I'm going to add to that the outer product between key 2 and value 2. And I'm going to add to that key 3, value 3. Okay? So why does that give us a database? So that gives us a database. And what we want to do is we want that if we go to the database and we query it with the query, and this is going to be a matrix multiplication, right? The database is going to be a matrix. We want, and let's say the query is key 2, we want that we get value 2. it's magic, right? I can just add these things to the database with a plus, and you can see I can also update that in the future by simply adding to the database one of these outer products. And we want this. It seems a bit like magic, but here is how it works. And the condition is that all of the keys are orthogonal to one another. If the keys are orthogonal to one another, this is going to work because imagine we now go to the database and we multiply by q. What does that do? That is going to be key 1. We can write this as a sum, right? We have this sum over the I of key I, value outer product with value I, times q. Now that we can pull in the q, so we're going to have the sum of I, and here we're going to have the key times the value. And this all times q. Now q is going to be, as we said, q is one of the keys because we queried the database with one of the keys. So here it's going to be key number 2 with key I, and this is an inner product right here, and this is an outer product with the value I. Now, if the keys are orthogonal, you're going to see pretty quickly that if I is equal to to 2, then this is going to be just the number 1, if they are orthogonal and normalized. Right? If the keys, however, are not equal, so if I is anything else than 2, this is going to be 0. And magically, all of the things drop away, all of the sum elements drop away, except the one that contains vi or v2. So this is going to get v2. So magic. And as we said, the conditions are that the keys are orthogonal to one another and normalized if you want. But this gives you now the flexibility. If your embeddings are meaningful, meaning that the latent space is meaningful, you can also query. Your queue can be kind of a superposition of keys or something in between the keys. And what you'll retrieve is an interpolation of the values. And this is very, very similar to the attention mechanisms we have nowadays, right? These queries and the keys and the values. And this paper is going to establish how exactly this is similar. Another similarity, by the way, to attention mechanism is exactly this fast wait principle. I've always said that an attention layer is essentially a fully connected layer, but the weights aren't learned. The weights are dynamically produced by another mechanism depending on the input. And this is exactly this fast wait concept. So it makes total sense that there is a connection. And it also obviously makes total sense that someone already invented this in the 90s, as I think that's a meme by now. Right, so how do we make the connection between attention mechanism and these fast wait modules? So here's how we do it. First, this is the attention mechanism as we know it. It's just written a bit differently in the specific context of autoregressive transformers or autoregressive attention mechanisms. So we don't care about how we do all the queries, keys, and values. We care about how do we produce the queries, keys, and values of the very last step, because in autoregressive transformers, what you have as a limitation is this causal attention. So if you have your sequence and in a self-attention or in a, let's say, non-autoregressive setting, you would have attention from each element to each element. So all the queries can attend to all the keys. However, in a causal attention layer, let's just build a causal attention layer on top here of the non-causal attention, which makes absolutely no sense, but every single query can only attend to keys that are in the past. So this can attend to here, and now I'm drawing the arrows in a different direction, but you see what I mean. You can only attend to things that are in the past. And technically, it is too much of a constraint, because if you have multiple layers and you think of what does it mean to be autoregressive? What it means to be autoregressive is that you want to produce the next element. So if you have a stack of layers, you want to produce this element right here. It is perfectly conceivable that the information in your network can flow from this element, which is maybe the noun in the sentence, to the verb of the sentence here, to the subject of the sentence here, and then to the front again, or to here again, as long as you don't draw information from over here, from the future. You're good, right? But technically within one context window, it is technically allowed to send information around like this. Now, the problem with this is we can't easily parallelizably train things like this. So what we do is we simply restrict in each layer the attention to only attend to things in the past, which means that we end up with kind of these attention sort of like cones where you can only send information forward and not backward, even within a layer, even though it's technically allowed. So this restriction is also encapsulated in this formulation. So we're going to ask ourselves, how do we produce the current output yi? The current output is going to be produced by simply looking at the current query, because all the past queries we've already computed in the last steps, right? So we simply need the current query, but we need all the values and all the keys, right? The V and the K being capital here means that they are the accumulation of everything in the past. This is exactly what we've said. You can, in fact, attend to all the past, but not the future. So the current output is going to be produced by the current query attending to all of the past. The past here is constructed, you can see in each time step, what we're going to do is we're going to compute the current key and value, and we're going to concatenate that with the past keys and values that we've already computed. There's no need to compute things twice here, so that's, in each time step we simply need to compute the current queries, keys and values, and the keys and values we're going to accumulate into these matrices by concatenating them. Now, if we slide, usually this extends the sequence like this, right? We extend and extend and extend and extend. Transformers have a limited size window, so eventually these things here are going to drop away, in which case these matrices here are going to not be concatenated but kind of shifted towards the right. But that is a minor detail. And the queries, keys, and values are simply going to be produced by the learned matrices here, like this is. So this is very standard transformer, or very standard attention mechanism. Okay, now they say, look here, so here we have the softmax, and the softmax is pretty intrinsic to the attention mechanism, because otherwise it would just be a linear transformation. So the softmax, what the softmax is going to do, once the query attends to all the keys, we're going to normalize that using a softmax, which basically gives you a distribution over the input sequence. So you don't want to know you want to know where should I attend in proportion to everywhere else. So there's a normalization involved, and of course also the nonlinearity in the softmax, but the real bottleneck is the normalization. So first they say, what happens if we just leave away the softmax? And this is a rederivation from other papers, by the way. This is they're just building their case here. So what happens if we leave away the softmax? If we leave away the softmax, we simply have, here is the key query, here is the attention, and that is going to be multiplied by the values. Now, we can rewrite this a bit. Actually, it comes from here. Here is the attention matrix. This is the attention matrix for the current time step I, right? Just for the last query. And that's going to be multiplied by the values, and that gives you your output. So the attention matrix tells you how you need to aggregate. The values tell you what the value of the things you aggregate are, and you do a weighted accumulation it gives you your output. If you rewrite this a little bit, you can clearly see that instead of an inner product between the keys and the queries, then being multiplied by the values, you can as well write this as an outer product between the values and the keys, and then a multiplication by the query. And this should, be familiar to you by now. So here you can write this as an outer product of the individual keys and values of the past, and then the queries. And this here is exactly this database we talked about, actually, with the sum, including the sum. So this is the database of the past. And now you can see the connection to these fast wait algorithms. I mean, it looks exactly the same, except it has the fast wait also had this kind of sigmoid in it. But essentially, you're building this matrix. So the matrix is going to be multiplied not by x directly, but by q, which is a linear transformation of x. So that's pretty similar. So this is what they call wi. And your output is simply going to be a linear function of the input, so to say. And it is also going to be a query into this distributed database. So they say we can further rewrite these equations such that they directly relate to these fast wait equations. So you can build this up step by step instead of building the whole sum. What you can do is you can simply write this wi here as a decomposition into the wi from the last step. Simply add the current outer product to it between values and keys, and then you have your current fast waits, your current database that you then query by q. So this relates it to the fast wait algorithm. Now we made a crucial step in that we left away the softmax, right? And that now we're going to have to fix that. So this has already been done, like we've already come this far, and I've made a video about the performer. So the performer reaches this point, and then they say, okay, now instead of leaving away the softmax, we can generalize. We can generalize the softmax by writing it as a sort of kernel. By writing the softmax explicitly, equation 7 can be written as, so this is the full equation, equation 7 is the full with the softmax attention, can be written as this. And this is a bit tricky. So K is a kernel, and the kernel in this case is the exponential function. The softmax is going to be this part right here. So it involves this and is going to be normalized, right? The softmax has the exponential function and it has the normalization. So this is going to be the softmax part and then simply multiplied by the values over here and aggregated. Okay, so you can write it as such, and then you can think about, okay, what kind of kernel could we substitute to approximate the softmax, but without having, kind of the pesky nonlinear things. So if you know anything about kernels, which I don't, but there is a good Street Talk episode, which I'll link, where I got to ask all the dumb questions about kernels. I hope that helps. But every kernel represents an inner product in some kind of space. So every kernel can be implicitly written or explicitly written as this inner product in some kind of space, and phi here is the function that maps you to that space. And the performer thought, can we find? So the performer explicitly showed which phi you have to choose in order such that if you plug it in to this kernel, it gives you back the softmax. And that turned out to be an infinitely large space, so like a non-computable function. But then they asked themselves, can we substitute? Can we approximate that kernel with a finite function, phi, right here? And that is the performer paper. It's very theoretically grounded, but it has some problems, and they discuss the problems here. But first, see, if you write the kernel as such an inner product, and which you could actually compute, you can then, you can see here, this bracket is the problem. This and this. Since the kernel is nonlinear, you cannot just pull these things apart. However, if you write the kernel as the inner product, if you know what the phi is, you can write it as such and pull it apart. And then you can do the same transformations as here. So you can see that here it's an inner product, but if this is linear, you can also see this as first the outer product of the key mapped through the phi function with the value. So there's an outer product, and only then multiplied by the query. And you can as well see the normalization as an accumulation of these keys, and only then you multiply the query in here. So this gives you the benefit that not in each step you have to compute these things. In fact, you can accumulate these things across the time steps. They make this explicit here, write it as an explicit outer product. You can see it is the same thing again, where you can build this database from the past. So it's not value times key, but it's value times phi of the key. And for the normalization, you can equally build up this accumulator on the bottom right here. So that's going to be your z variable. You can see that this pretty much results in the same algorithm, except that we also keep track of the normalization here, which we can do just as we build the fast weights, we can accumulate the normalization. I believe this was already also discussed in the Performer paper, but it's pretty cool to see here that everything leads to the same path. So first we went from fast weights, then we looked at transformers without the softmax, and we said, oh, if this is linear, then there is a clear connection to fast weights. And now we say, okay, if it's not linear, but if the kernel, if we can find an explicit kernel, then we can write it as a linearly decomposable thing, and then it's also a fast weight algorithm modulo the normalization down here, which I guess would still count as a fast weight algorithm. So they say essentially these linear transformers are fast weight algorithms, specifically in the autoregressive case, right? Always think that this is in the autoregressive case because the specific constraint of how we train autoregressive models with the causal attention mask gives rise to being able to write the algorithm like they do here. So they discuss this capacity limitation now. While the softmax is super nonlinear and normalizes and all of that, it sort of is not subject to these capacity limitations, but it is subject to other capacity limitations. But if this is linear, if this is now a linear algorithm, they say endlessly adding new associations to a memory, that's the database, of finite size, and as in equation 17, inevitably will reach a limit. In linear attention, information is stored in a matrix and is retrieved using matrix multiplication. As a consequence, to prevent associations from interfering with each other upon retrieval, the respective keys need to be orthogonal. Otherwise, the dot product will attend to more than one key and return a linear combination of values. With keys embedded in a d dot space, d dot here is the space of the inner product, there cannot be more than d dot orthogonal vectors. That is, storing more than d dot associations will result in a retrieval error. In linear transformers, when the length of the sequence is longer than d dot, the model might be in such an overcapacity regime. So now they say, since these linear transformers are all fast weight algorithms, they have these capacity limitations. Right? They built this linear database with outer products. So technically, they can only store a finite, and finite given by the dimensionality amount of distinct data points. Now, this is a very special way of looking at these things, and we're going to see later what they do, so in their experiments, I can tell you right now, in their experiments what they do is they have a sequence of random keys together with constructed values. So the values are kind of orthogonal unit vectors, but the keys have to be learned, but they are, so let them be fixed set of keys, sorry, not the keys have to be learned, the embeddings have to be learned. Let them be finite and fixed sets of keys and values, okay, and they are sampled randomly. So they're going to produce key value pairs randomly with random keys and fixed values, and they see whether or not they can store and then retrieve an arbitrary one from that database. Q is randomly chosen to be one of the L keys. So we store L elements that we sample at random, and then we see, can we retrieve one of them? Now this isn't exactly what we want in transformers. This is a very special way. It's a very computational way of looking at things like, okay, what's the memory capacity here? How many distinct things can we store? What we want in transformers is more, we're not interested in storing everything accurately, but I think we explicitly want this interpolation in transformers. It is very useful to look at these mechanisms from this kind of synthetic setting where we really test the memory capacity, but it's important to keep in mind that that is not ultimately what we want. Ultimately, we explicitly want those superpositions to occur, because in NLP we have synonyms, like we have same information from different words, we have words in between other words, and so on. So it is not exactly, the criticism here is valid, but it is not exactly in the wound of what's hurting in transformers. Nevertheless, they say, can we improve this update rule? They say linear transformers can end up in this overcapacity regime where they need to store more things than their dimensionality allows. If the sequence length L exceeds the dimension of the keys. Once in overcapacity, an ideal memory model should dynamically interact with the memory contents and selectively determine which associations to remember and to forget. So they criticize transformers here in saying, with this update rule where we only ever concatenate, right? We have the key and we concatenate the new key right here, and so on. Now, irrespective of whether we limit the sequence length right here, if the sequence and we drop things here, if the sequence length we consider is higher than the dimensionality, we're bound to have keys that conflict with each other. And so they say, when you add a new key, given that you are bound to override each other, you should be able to sort of dynamically add keys and not only concatenate to a fixed set. Now, what they're going to do is actually not change the keys, but they're going to change the values. And this is something I find pretty cool, because you also concatenate the value onto this. But what they're going to say is that instead of just appending the keys and the values, what we're going to do is, since this key is going to conflict with one key that's in here, at least, let's say it's going to conflict with one key, what we're going to do is we're not going to store the actual value to this key. We're going to store the diff in value between this key and the key that it's conflicting with. Maybe they're not fully overlapping. Maybe this key is a little bit off that key, but mostly. So, if we enter this key and we would just store naively the value, we would also retrieve the value associated with the other key because we overlap. And then we'd get like a superposition of the two values and so on. So what we should do is, instead of storing the value, we should store the diff between the value, the old value, and the new value. And then when we retrieve and inevitably overlap, we're going to retrieve, right? We're going to retrieve the old value and we're going to retrieve the new value, but now that's the diff. So plus, other way around. So we're going to store this plus v, and since we've stored the diff, this cancels out. and we only have the new value. That's pretty cool. Yeah, so instead of actually storing the diff, they say, the network should be able to say how much it wants to update that value. So the network is going to also output a number beta that is, as you can see here, computed from the input by a little one-layer neural network. And what you're going to do is you're going to first retrieve the value that is associated with the key that you want to put in. So this value here that's the old value, because this key probably overlaps with something. So you're going to use that key as a query into the database, retrieve the value that's associated before. Then you're going to interpolate the old value and the new value, and that's what you're going to store. And that turns out to be like this. So you generate the new database from the old database, plus here the diff, that's the diff between the values, weighted by a factor saying how much really you want to update that. Because of course, also when you input the old key, you're going to retrieve the new value. So you might be, you might not want to just slam in the new value because of course the old value isn't updated yet. So, this gives you sort of a handle on that. All right. And then, of course, you simply retrieve the new thing with the query. And now if the query is a key that's overlapping, you're going to retrieve the old value and you're going to retrieve this weighted update on top of that. Very cool. They also discuss different normalization strategies. So one normalization strategy, because we also have this denominator in the softmax, right? And if they simply do these accumulations, as we saw on top, right? If they simply compute this and they compute this using the accumulation technique, like an accumulators, they are bound to sort of explode, because also these kernels, they map things to positive space. So things explode. So what they say is we should change our phi here to be the phi divided by just sort of the sum of the entries. So this is an easy normalization you can do independent of anything else, and it keeps the values in check. The last thing they do is they now suggest a phi. So, given that they've criticized things, they say, okay, let's look at the phis that are already around that would meet our requirements. So we're looking for a function that acts as a mapping to the space of inner products that is going to replace the kernel. So one suggestion here is to use elu plus 1, which is fairly easy, but it has some disadvantages. Namely, importantly, as an element-wise function, preserves the dimension of the input key vector without modifying the memory capacity as discussed. So this, not only is this not the softmax, it also doesn't, is actually problematic because you have no handle on the memory capacity. The reasoning here is that if you want to go from nonlinear with, technically infinite capacity or whatever nonlinear bound, if you want to go to linear, which has a clear upper bound on the capacity, you need to have kind of a hyperparameter where you can artificially increase that capacity to make up for the fact that you're going to linear space. This doesn't have it, even though it's super easy. On the other hand, Favor Plus, which is the algorithm from the performer, has that, but it relies on kind of random sampling from a normal distribution, and it also relies on kind of complicated, it's not super complicated, but it is mathematically actually rigorous. If you go into enough dimensions, you will accurately approximate the soft max. But you need random features for that, and these random features can, either hurt your it can hurt your performance if you happen to sample them in a bad way, and you sample them once per training run, or per model, so you don't have do-overs in that. I guess you can train again, but So they suggest a thing that is easy and you have a handle on the dimensionality. So they say we consider 4 different keys, right? If we have 4 different keys in R2, they are going to, so the keys are in 2 dimensions. What they're going to do is they're going to construct a mapping into 4 dimensions such that they have the highest possible chance of, if 2 keys are different, they're going to be orthogonal to each other in that higher space. Now, they're going to do this as this. So these are the 4 dimensions of the mapping. This is going to be a vector at the end of these 5 functions. And the R is ReLU. So what they're going to do, if they're going to take a key and they're going to multiply simply the positive part of the dimensions, the negative parts, and the cross parts right here to get the 4 features. Which means that a given key can only be non-zero in one of those 4 things, right? Like either your first coordinate is positive or negative, or your second coordinate is also positive or negative. That gives you 4 possibilities. And the construction here makes it such that only one of those 4 entries is non-zero, depending on which section you are. You can see that right here. These are the 4 sections. So if your vector is right here, it's going to be non-zero in the blue component, but not in the green, orange, or purple components. So they say this gives you kind of maximal, if two keys are in the same quadrant, yes, they're going to overlap in that higher dimensional space, but if 2 keys are in different quadrants, they're going to be guaranteed orthogonal. They extend this to here, so they're going to say, we're going to choose this parameter nu here, which that is going to be the handle on our dimensionality. So nu is setting nu is upgrading your dimensionality of the mapping. If nu is equal to 1, you keep the dimensionality of your key. Actually, you double it. But you can set it to 2, or actually they only ever go to 3. 3 is as high as they go. So they make the intrinsic dimension 3 times higher than the original dimension at maximum. So what are they going to do? They're simply going to take the vector here of positive and negative elements of your key, and they're going to so for entry I, they're going to choose the entry I, and they're going to multiply that with, again, the ReLU of some other coordinate of the same key. So you're simply taking 2 coordinates, take the ReLU of them, you multiply them together. If you include the negative parts of the vector, that gives you exactly what we've seen up here. And the nu gives you saying like how many different coordinates do you want to multiply. So if nu is 1, you simply multiply coordinates 1 and 2, and then 2 and 3, and then 3 and 4, 4 and 5, and so on until you're once around. If nu is 2, you do all of that, but also you concatenate that with 1 and 3, 2 and 4, 3 and 5, and so on. Now, at the end, they wrap around. Like the last one would be like 10 and 1. They say they have code for this. It's pretty easy. You simply kind of roll around the vector and then ReLU it and then multiply it. Or first ReLU. First concatenate the positive and negative parts, ReLU that, and roll and then multiply. They say this gives you in this upper dimension 2 times the dimensionality of the key, 2 because you have the positive and negative elements, times the dimensionality of the key times nu. Now this only works, actually, so this is wrong. I believe this is wrong right here. Here, they say you can choose nu to be any of these values, which is not correct, because if nu is higher than, I believe, what's d key 2 divided by 2, so if it's higher than d key, then you're going to have duplicate elements, because if you consider this here and you view it as a matrix that you later unroll, right, as the projection up, you have I, and you have I you have new here, and what you can have is at maximum, this is I plus new, right? You can have I attending, you can have 1 attending to 2, you can have 1 attending to 2 and 3, you can have 1 attending to 2, 3, and 4, but at some point, if, and then you have to have 2 attending to, so you can have 1 attending to this. 2 cannot attend to 2, but it can attend to 3, 4, 5, or attend to. It can be multiplied with this. 3 can be multiplied by 4, 5, 6, and so on. And since you roll around, their code actually rolls around, so it goes around here, you can easily see that now if new is equal to the full 2 minus 1, to the full dimensionality of the matrix here, then this element is going to be the same as this element, because it's going to be, the first one is going to be K1 and K2, and then in the second one, because you roll around, it's going to be K2 and K1, which is going to be the same. So just a little mistake in how you can choose. Nevertheless, they never get up there. They go 1, 2, or 3, and they never even get close to that being a problem. All right, so I've already told you the experiments they do, where they try to retrieve random values, and I've already tried what kind of problem I have with that. Nevertheless, they show here that the linear, and I'm sorry, this is super pixelish. I'm going to try to fix that in the future. The linear transformer, as you can see, it has so here is the number of unique keys that you can store. The lower your curve, the better. So these are the mistakes. This is the loss that you make. So the linear one, the dimensionality is 64 of the keys. So you would expect that it can store up to 64 keys well, and then it can't store more, it gets conflicts. And that's exactly what you see. So here you start off no loss, and then at around 60, the loss shoots up because you get into conflicts. Interestingly, these favor the performer algorithm shoots up immediately. And that's, probably because it's not built for this specific purpose. They try it with quite a high number of random features, but it's pretty interesting to see. Whereas their method, so if they choose new equals to 1, it goes for double, which you would exactly expect. So if new is equal to 1, the dimensionality of their algorithm is 2 times the dimensionality of the keys. So after 120 some, the loss shoots up. If you choose new to be 2, then after, you can see right here, after 240 some, you shoot up, and if you choose new equals to 3, after 360. While the softmax, it gets into the error rates here, but this is a different regime of bounds. We cannot analyze this with the linear bounds we derive, because this is the highly nonlinear, highly infinite dimensional implicitly softmax. This is pretty cool. As I said, even though it's not exactly what we want from our attention mechanisms, but it's cool to look at them in this way. They do a bunch of other experiments, and they actually do language modeling. So they do machine translation. And machine translation, it's not really an autoregressive problem per se. I mean, it is, but you always have the input sentence, and then you have the output sentence, and only the output sentence is autoregressive and not the input sentence. But still, you can actually formulate it as an autoregressive problem. And if you only do causal attention in this part, I don't know how much that hurts you, but technically you don't need to. The original transformer, I think, didn't do that. It did full attention in the input and then causal attention in the output. So here they show that in the intermediate dimensions, they outperform the performer, but if you go to higher dimensions, the performer outperforms them. However, in language model experiment, so this is perplexity, so lower is better. In language model experiment, no, sorry, they here they compare update rules, like they compare update rules, plugging it into the different transformers. So they show that their update rule is better than just the sum update rule in the linear transformer and in the performer. So here you can see the number of trainable parameters, yada, 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 in our update rule, respectively, for the small and medium configurations. So, interestingly enough, also, there's yet more evidence that you might not need position encodings if you have an autoregressive models, which is quite astonishing. But if it's autoregressive, I can sort of understand it because it kind of acts like an RNN, and an RNN can intrinsically build a counter in the, they build a counter inside the update mechanism. So I don't want to go too much into the experiments right here. You can look at them. They are, let's say, they're promising in terms of real applications, and it's definitely worth checking this out if you are in an autoregressive problems. Though where it really shines is where you really have kind of a sequential task and need to remember symbolic information. Might not necessarily be super applicable to language that has, it's not really distinct symbols, right? There is interpolations and so on. So that would be my comments on this paper. Video is already too long. Thank you very much for listening. I'll see you next time.